Quick question. What did Einstein actually win his Nobel Prize for? If you said relativity, that's the most common wrong answer in physics. He was nominated for the Nobel Prize 62 times between 1910 and 1921, almost entirely for relativity. He never won it for that, not once. He won it for something that's 1887, a physics lab in Karlsruhe, Germany. Heinrich Hertz is busy proving something huge, that invisible electromagnetic waves, predicted purely on paper by James Clerk Maxwell decades earlier, are actually real. His setup is simple. Two metal spheres with a small gap between them. Crank up the voltage and a spark jumps across. But Hertz notices something odd. Shine ultraviolet light on the metal spheres and the spark jumps more easily, as if the light itself is somehow helping the electricity along. He doesn't chase it. He's about to make history proving radio waves exist. That alone will make him famous. He notes the strange little effect and moves on. Hertz dies just 7 years later, at only 36. He never finds out that his throwaway observation is about to become one of the biggest unsolved problems in physics. A year later, 1888, physicist Wilhelm Hallwachs picks up the thread. He charges a freshly cleaned zinc plate negatively, shines ultraviolet light on it, and the negative charge doesn't just weaken, it disappears, as if the light is physically knocking the charge off the metal. Over the next 15 years, Hallwachs and later Philipp Lenard study this properly, and what they find doesn't just seem strange, it breaks physics. Here's why. In 1900, everyone agrees light is a wave. Waves carry energy the way ocean waves carry energy, spread out, continuous, building up over time. Based on that, three things should be true. 1. Brighter light should knock electrons out with more energy. A bigger wave should hit. The first hint of an answer comes from a completely different problem. In 1900, Max Planck is trying to explain why hot objects glow the colors they do, a puzzle so broken that the accepted wave equations predicted every hot object should blast out infinite energy. Planck finds a fix, but he doesn't like it. What if energy isn't smooth and continuous, but comes in small, fixed-size packets? He called 1905. Not a grand physics institute, a patent office in Bern, Switzerland, where a 26-year-old clerk evaluates other people's inventions for a living. No wild white hair yet. No fame. Just a notebook. And 4 papers he's about to publish in a single year that will each reshape physics. His name is Albert Einstein. Einstein takes Planck's quantum idea and does what Planck himself was too cautious to do. He says light itself is made of these packets. Not just emitted or absorbed in chunks. Light is chunks. Tiny bundles of energy, each carrying an amount fixed only by its frequency. E equals h times f. Higher frequency, like violet or UV light, means a bigger energy punch per packet. Lower frequency, like red light, means a smaller punch, no matter how many packets you throw at it. Suddenly, all 3 impossible facts make sense. An electron isn't slowly collecting energy from a spread-out wave. It's being hit by one packet at a time, like a single ball thrown at it. If that one packet doesn't carry enough energy to knock the electron free, it doesn't matter how many arrive per second. Nothing happens. That's the threshold frequency. If it does carry enough energy, the electron gets knocked out instantly, with no waiting around. And cranking up the intensity just means more packets per second. More electrons total, but each individual one is still hit by exactly one packet, so its energy doesn't change. Here's the twist nobody expects. Almost no one believes Einstein, including the man who ends up proving him right. American physicist Robert Millikan thinks the whole light is made of particles idea is close to absurd. In his own 1916 paper, he calls Einstein's hypothesis, in his actual words, bold, not to say reckless, because it seemed to contradict decades of rock-solid proof that light behaves like a wave. So Millikan sets out to break Einstein's equation in the lab. He spends nearly 10 years building increasingly precise vacuum apparatus, testing metal after metal. Instead of breaking it, 1921, the Nobel Committee finally decides to honor Einstein. But there's a catch. General relativity, his most famous work, is still considered too new and too disputed to reward. So the prize goes specifically to his explanation of the photoelectric effect instead. Einstein doesn't even attend the ceremony. He's traveling through Japan when it's announced, and a German ambassador accepts it on his behalf. When he finally delivers his official Nobel lecture, over a year later, he talks about relativity anyway. 2 years after that. Okay, history lesson over. Let's turn this into the actual equation your exam will ask for. Every photon carries energy, E equals h times nu, Planck's constant multiplied by frequency. When one photon hits one electron inside a metal, part of that energy is spent just breaking the electron free from the metal's surface. Every metal has its own minimum breakout energy. Physicists call it the work function, written phi or W0. Metals like cesium and sodium have a low work function, which is exactly why they're used inside light meters and photocells. Even ordinary visible light carries enough energy to push electrons out. Metals like platinum have a higher work function, so they need higher frequency light, sometimes UV, before any electron is released at all. Now here's the payoff. Remember our 3 impossible facts from earlier? Watch this one equation dissolve every single one of them. Fact 1. Brighter light should mean more energetic electrons. False, because intensity doesn't even appear in the equation. Only frequency decides an electron's energy. More intensity just means more photons per second, so more electrons total, but each one is still hit by exactly one photon, so its individual energy never changes. That's why photoelectric current is directly proportional to intensity, but maximum kinetic energy isn't. Fact 2. Any frequency should work if it's bright enough. False, because if h nu is smaller than phi, there simply isn't enough energy in a single photon to pay the exit fee, no matter how many arrive per second. That gives us the threshold frequency, nu 0, the exact point where h nu 0 equals phi, the bare minimum entry ticket. Below it, nothing. Not one electron, ever. Fact 3. Dim light should need time to work. False. The interaction is one photon, one electron, instantly. There's no waiting for energy to build up, because energy was never accumulating in the first place. One equation, 3 impossible facts. Solved. So how do physicists actually measure this in the lab? Using something called stopping potential. After electrons are knocked loose, apply a small reverse voltage that pushes them backward. Slowly increase it until even the single fastest. That gives you 3 graphs that show up constantly in exams. Graph 1, photocurrent against intensity at a fixed frequency, a straight line through the origin. Double the intensity, double the current. Graph 2, photocurrent against retarding voltage. Current drops gradually as reverse voltage increases, hitting 0 exactly at V0. Run it at 2 different intensities, same frequency. Both curves hit 0 at the same stopping potential, but the higher intensity curve sits higher up. Graph 3, and this is the one that actually convinced the world Einstein was right, stopping potential against frequency, a straight line. Its slope is h divided by E, a fixed number, identical for every metal on Earth. Where the line crosses the x-axis is your threshold frequency, nu 0. Different metals shift the line left or right, but the slope never changes. When Millikan plotted this graph from real data in 1916, the slope matched Einstein's prediction almost exactly. That graph is the moment the particle theory of light stopped being a guess. Quick worked example, the kind you'll actually see on paper. Sodium's work function is about 2.3 electron volts. Shine UV light of wavelength 300 nanometers on it. Using the shortcut Hc equals 1240 electron volt nanometers, photon energy works out to about 4.13 electron volts. Subtract the 2.3 electron volt work function, and maximum kinetic energy is about 1.83 electron volts. This isn't textbook trivia. It's running in your pocket right now. Solar panels use a close cousin of this idea. The photovoltaic effect, where photons free electrons inside a semiconductor instead of a metal surface. Same core insight, light delivering energy in fixed packets. Automatic streetlights and burglar alarms use photocells that react the instant a light beam is broken. Old cinema film carried its soundtrack as patterns of light down the edge of the reel, read by a photocell to reproduce audio decades before digital sound. Night vision devices and hospital PET scanners use photomultiplier tubes built to detect single photons at a time, the most sensitive light detectors ever built, running on the exact effect Hertz stumbled into by accident in 1887. So next time someone tells you Einstein's most famous idea was relativity, tell them about a patent clerk who looked at a century-old lab curiosity, realized light comes in pieces, and rewrote how we understand it, one photon at a time. But if light can behave like a particle, does that mean particles can behave like waves? That's exactly the question a French physicist named Louis de Broglie asked next, and the answer is even stranger. That's the next video. If this made your physics chapter click, hit subscribe, and comment if you want the numericals broken down in even more depth.